Okay, so our topic today is going to be Unit 2.4, and this is day 1, and we're going to be talking about polynomial functions. So we've already looked at polynomials as functions, or not necessarily functions, but as equations, and we've looked at polynomials as just expressions by themselves, but not actually looked at them and how they act as functions, and we'll see some similarities and some differences with how we've worked with them in the past. So our objective today is to simply describe the characteristics of and graph polynomial functions given the vertex form and standard forms. So the idea is that we're going to be able to describe a polynomial function by just looking at the equation, and similar to what we've done in the past with our linear, with our quadratics, and with our absolute values, we'll be able to identify certain pieces of the graph without actually looking at them on a graphing calculator or plotting them out. So we have our three different forms. So the first form is our parent function, in which we have a f of x equals x to the power of n. Now, one thing that we have to look at is that n needs to be what we call an integer. Now, if you remember any of your number system or anything like that, an integer is a positive or negative whole number. And so as long as it's one of those values, so it's a positive or negative whole number, we're going to be in good shape to create what we call our polynomial functions. And so as we look at our vertex form, we'll notice some similarities here with the vertex forms that we've already worked with. Notice that really the one big difference between this form and the quadratic form, instead of a power of 2, we're going to have a power of n. So basically we can pretty much substitute any whole number, positive or negative, that we would like to into this value. Now we're really going to only be working with positive values, so when we talk about n, we want to really look at this in terms of positive whole numbers rather than negative whole numbers at this point. But the idea is that it can be both. But anyway, we can see some similarities here in which we're going to still be working with those particular values that we have been before of a, h, and k. And you might even be able to guess the reason that we call this vertex form is that our vertex form still gives us our vertex of h comma k. Doesn't even actually matter what that exponent is, it still gives us our vertex form. And then finally we have our standard form, and we'll talk a little bit about our standard form. But what we have to kind of understand here is that we're going to start with some number, and then every term below that in terms of standard form will be decreasing its power by 1 from the regular, or from the original. And then so that's why we're subtracting 1, subtracting 2, subtracting 3. So for example, if this was x to the 6th, then it would be x to the 5th, x to the 4th, x to the 3rd, and then so on until you get down to this value here, which we'll call a constant. And so the idea there is that it just shows you that it decreases in value from the original or the largest exponent all the way down until you get to a constant. And so first of all, we're going to look at what's so special about our standard form. So we've kind of talked about standard form already. But the idea of what our standard form is going to tell us is a couple of things. So first of all, this is going to tell us our degree of our polynomial. So just like we did before, the degree of a polynomial is always the largest degree. And in standard form, this first term tells us what the degree is, or what the largest degree is. And that's going to tell us whether this is an odd polynomial or an even polynomial, and we'll get into what that specifically means. It's going to also tell us a, which a is going to be what we call our leading coefficient. Now, leading coefficients are actually important. These will help us with our n behaviors. And so we're going to kind of bring up those n behaviors again. But the idea is the leading coefficient will tell us that information. And then here, as we go along, and as I showed you in the last slide, we start with some degree, and then we keep going down until we get to, x, or x squared, x, and then eventually we get to a constant. Now, what we just kind of have to do here is I'm just labeling it with this capital C to show that it's a constant. But eventually this constant is going to represent our y-intercept. So just like in most standard forms, our y-intercept is going to be that constant at the very end. So we have a bunch of variable terms, it's just that eventually we'll get there, and if it's not there, we can just assume that it's 0, but whatever that value is going to be our y-intercept. So standard form tells us our degree, whether it's odd or even. It tells us our leading coefficient, what we're going to want to know, and it also tells us our y-intercept. And so, some of this stuff in the middle, it's not really going to tell us a whole lot. It'll tell us how the graph will change, shape and everything like that, and so we'll look at the shape of these, but the idea is that standard form tells us these things. Now, as far as also with degree, this will tell us our number of x-intercepts too as well, or what we call our zeros. And so we'll look at those in just a moment too as well. The next thing that we've kind of talked about before is our vertex form. And so from our vertex form, it kind of tells us the same thing as our standard form, just in a little bit different way. First of all, this is still our degree, so when we see that exponent of n, whatever that is, that's going to end up being our degree. I kind of already told you that it still gives us our vertex of h comma k, so that would still be the same. So we've been working with vertex form, and the reason that we work with vertex form is because all these functions that we're going to be working with have some form of h and k that we can create this vertex for. And so this is going to at least tell us our vertex form. A, similar to the standard form, will tell us our leading coefficient. And so, we're going to use that, like I said, with our n behavior, but the leading coefficient at least tells us a little bit more. Now we can also talk about how this means that it's a stretch or a shrink from our original value and tells us whether it's reflected. So those still apply to our vertex form. Now the only problem with vertex form is it does not give us our y-intercept. So we can't just say that k is our y-intercept. If we wanted to find our y-intercept, all we would have to do is take x and set it equal to 0. If you wanted to find your y-intercept, y-intercept. And so the idea there is that our vertex form will still tell us the same things, it's just now that we have to pay attention to the exponent, this n, to tell us our degree, whether it's odd or even, and what our n behaviors are. And so those are our two forms. And so now we're going to look at what it means to be an odd polynomial, what it means to be an even polynomial. So here I have an example of an odd polynomial. Now the reason that this is odd, and you can kind of probably predict here, if we look at our leading coefficient or our leading term here, we have x to the 5th. 5 is odd. And we've kind of talked about odd and even already. But the idea here is that 5 is odd, so this is an odd polynomial. Now, what this will tell us is that will kind of tell us what our n behaviors are. And if you look at this, this is kind of just an example of a very simple polynomial function. It's got a lot of ups and downs, it's got a lot of vertices and things like that that we've kind of been working with. And so first of all, we can simply just look at our n behavior. If we have a positive leading coefficient with what we do here, remember with odd degrees, our n behavior is different, meaning that it's either going to be up and down or down and up. And we've kind of already looked at this with polynomials. We've kind of looked at those n behaviors, and that's not going to be any different than what we're doing here. So if we have a positive leading coefficient, as x goes to the right to positive infinity, that means that y is also going to go to positive infinity. And if x goes to negative infinity, y is going to go also to negative infinity. Now the reason that I know that is, first of all, that these are opposite from each other, but imagine that this one down here, this actually has a positive coefficient, this equation down here. If I was to plug in a positive number into this, and it was a really large positive number, my numbers would be positive because this particular exponent would win versus the rest of those. But if you think about this, as I move in this direction, this graph is going up. And as I move backwards, my graph is going down. Now with the negative coefficient, which I don't have shown, it's just the opposite here. So as x goes to positive infinity in the right, y is actually just going to go down to negative infinity. And as x goes to negative infinity, that means that y is going to actually go up. So the idea there is that it's our end behavior. Now we classified them as these ones here, that they're opposite from each other, that the end behavior is different. So as one goes up, the other one goes down. And our positive or our negative leading coefficient tells us how it ends. So as it moves to the right, it tells us what it's going to act like. And so the idea is we just kind of look at those end behaviors and still kind of classify those with what we've done before. And now we can look at what an even polynomial is. Now, with an even polynomial, we can talk about how our end behaviors is the same. And so when we have an even polynomial, things do exactly the same. Now we can kind of think about these and we can kind of look at the shape of these and kind of resemble certain things that we've dealt with before. But here I have an example of an even polynomial. Notice that the end behaviors are both going in the same direction. If they're going up, they're both going up. And if it's negative, they're both going to be going down. So with a positive leading coefficient, we can talk about how my values would be going up. And with the negative leading coefficient, they would go down. And so if I was to write these in terms of x and y, as x goes to positive infinity, y is going to also go to positive infinity. And as x goes to negative infinity, y is going to go to positive infinity. So it doesn't matter, the y's are still going to go in the same direction. Now with the negative leading coefficient, as x moves to the right at positive infinity, that means my graph is going to go down, which would be negative infinity. And as x would move to positive infinity, or I'm sorry, negative infinity, I'm really bad at writing infinities, I guess, y would also do the same thing and go to negative infinity. So the idea behind this is that we're looking at whether this is odd or even. It'll tell us the same things that we've talked about before with our end behaviors as either being the same or different. So if it's odd, it's different. If it's even, it's the same. And they're either ending positive, they're either ending negative, and that's what our leading coefficient tells us. It's kind of looking at only the right side of the graph, and if we can figure out the right side of the graph, then we can figure out the left side by either doing the same thing or doing the opposite. Alright, and so just a couple final points. And so what we should look for in every single function, it doesn't matter what the degree is. We'll always look for the degree. And the one thing that we want to look for is we want to decide what that degree is, and that tells us whether it's even or odd. So obviously if the number is even, the number is odd. The max number of zeros, we kind of touched on it a little bit, and we've kind of looked at this before, but the maximum number of zeros is the same as the degree. And so if my degree is 3, the number of maximum zeros that I could have is going to be 3. If it's 5, my maximum number of zeros is going to be 5. My end behavior, we kind of looked at that as far as our end behavior is concerned, but our three basic versions of that is that my end behavior is either going to be the same, so up, up, or down, down, or my end behavior is going to be down, up, or up and then down, and that's really just going to depend on what my degree is. So as far as my degree is concerned, what my leading coefficient is, that's going to have an impact on what my end behavior is going to be. And kind of going into that leading coefficient, it's going to be either positive or negative. And so what that helps us with is the leading coefficient tells us the right side or a positive x end behavior. So depending on what that leading coefficient is, we can always say that as x goes to positive infinity, it'll immediately tell us what y is going to go to. If the leading coefficient is positive, y will go to positive infinity. If the leading coefficient is negative, y will go to negative infinity. And then for the other one, we can either do the same thing or the opposite, depending on what the degree is. What we should also be looking for is either vertex form or standard form. Vertex form obviously tells us our vertex h, k, and we can identify a, h, and k, and we can describe the transformations that were applied. Standard form tells us everything that we have above there, but it also tells us our y-intercept. So we just have to be careful of what we can use and how we can use it in order to tell us all the things that we need. And that's going to do it for this video. And we're going to talk a little bit more about this in class as well.